we have a 2 kilogram box, which is released from rest at the top of a frictionless ramp. And then when it slides down the ramp and meets the flat surface, it encounters friction. The friction coefficient of the surface is 0.50. How far does it slide on that rough surface before stopping? So we're going to solve this a couple of different ways. We're going to solve it using our energy formulas and then using Newton's law and kinematics. And then we're going to compare to see which way is easier, because there are sometimes problems you'll get where you can solve it multiple ways, but there's going to be one way that is easier and is less work. So yeah, we'll get started on this. I'm going to move it over to the whiteboard. Okay. So our situation that we have here is that there is a ramp without friction and then a surface with friction, which I will draw as a messy line. Do that. The friction coefficient is 0.50. And we have a 2 kilogram box sliding down the ramp, and that the height equals 0.25 meters. So that is the information that we're given at the start of this problem. So given the fact that we're talking about energy, is there an equation that you think would be useful here, Bhavdeep?
Perhaps the conservation of energy could be used.
Right, so our conservation of energy equation would be potential energy initial plus kinetic energy initial plus work non-conserved is equal to potential final plus kinetic energy final. And just looking at the first part of this equation, are there any terms that you think we could cancel out?
Well, we got the kinetic energy is 0 since I believe it's released from rest and then it ends up at rest. So the kinetic energy initial and final should be 0.
Exactly. So we know that we're solving for the distance traveled before the box stops. So instantly that tells us that it will have 0 velocity at the end. And we know that it's starting from rest. So that also tells us that it has 0 velocity. And as we know that our kinetic energy equation is 1/2 mv squared, anything without velocity has no kinetic energy. For the second half of the equation, though, as we are on flat ground, and as we would most likely treat this ground as h equals 0, do we have any potential energy when it stops?
No, I don't think so. Since h is equal to 0, potential energy is mgh. So I doesn't think so.
Exactly. So just like we were using 1/2 mv squared for kinetic energy, our equation for potential gravitational is mgh. So h being the height, if there is no height, as in it's on flat ground, then we know that there must be no potential energy. So we're going to treat this as 0, which means that if we simplify this equation, we have potential initial is equal to negative work non-conserved. So that is a much simpler way of looking at this problem, and we got to that using our conservation of energy equation. So breaking this down into variables, we know that potential energy, as we just said, is mgh initial, and we have the mass of the block, we have gravity, and we know what the height initial was at 0.25 meters. But what is the work non-conserved equal to? What is an equation we could use for work?
It will only be the work done by a non-conservative force. So the only non-conservative force in this scenario is the friction. So
Exactly.
it would be frictional force times the distance it travels.
So work in general, the equation is force times distance. And seeing as we're looking at the work non-conserved, we can treat this as the work due to friction specifically, as that is the only non-conservative force in this problem. So it is the frictional force times the distance. And seeing as distance is what we're solving for, that's a good sign that we're on the right track. What is our equation for friction, Bhavdeep?
Equation for friction would be the negative of the coefficient of friction times the normal force.
Right. So our coefficient of friction times our normal force times distance. And why do we know that it's negative?
Since the force is acting against the motion, therefore we know the work is negative. And if we consider one direction to be positive, that is the direction of the motion, then anything that is repelling it should be negative.
Yes. So just if we were to draw, say, like a free body diagram of this, we know we have the normal force up, the weight down, and the only other force acting on it is the friction force, which acts in the negative direction. Therefore, when we're looking at it as a force, it is the negative friction times distance. And that's why we know that we have to have a negative there. And when we do our math later, we'll see that that works out when we're trying to solve for an answer. So rearranging this, we get that this is equal to negative mu times mg, as I know that the normal force is equal to weight from my free body diagram, and because it's on a flat surface. And this is equal to, times distance. So plugging this back in up here, we have the negatives cancel out, so it's mu mg times distance. And are these all variables that we have now, Bhavdeep?
Well, we got everything but the distance, so we should be able to solve easily for the distance.
Yeah, so the only variable we're missing is the distance. So if I cancel out mg, as it is present on both sides, I can say that the distance is equal to the height initial over mu. So that would be 0.25 meters over mu, which is unitless, and 0.50, giving us a distance traveled of half a meter. Okay, so that is our answer to the problem. It says, how far will it travel before stopping? We know it will travel half a meter. So we solved this using our energy equations. Now we're going to do it again using our kinematics and Newton's law equation, and see if it is more work, less work, and if we get the same answer, which we should.
So the next problem deals with springs and the conservation of energy. We have a block of mass 0.5 kilograms forced against a horizontal spring, and it compresses the spring, and then a certain distance, which is 0.2 meters. And when it's kind of released, then the spring decompresses and moves the box from its original position to 1 meter away from where it was. And we also got the spring constant, and we have to find the coefficient of kinetic friction between the block and the tabletop, because as it happens, the tabletop has friction.
Okay.
So let's get to solving that. All right, so I think the first thing we really want to do is just draw a figure of how the problem is set up. Just get a basic idea for how it looks when it's compressed against the spring, and when it's kind of away from the spring.
So I believe that K was equal to 1,000.
It was 100. Yeah.
100, sorry, Newton meters. And we know that when the spring is compressed, it's 0.2 meters. And the natural length of the spring when it is not compressed is 1 meter.
I believe 1 meter was the distance that the rock traveled.
Was that the distance? Oh, sorry. So 1 meter is the distance traveled.
And we also have the mass of the block, which is 0.5 kilograms.
Okay.
All right, so well, we need to find out the coefficient of friction, and the first thing that really comes to mind when something is pressed up against a spring is an energy equation. Well, the energy equation, as we discussed, or the conservation of energy equation, as we discussed in the previous problem, was U initial plus K initial plus work not conserved equals U final plus K final. And Freya, do you think that any of these quantities can be cancelled out?
I think that, as we can see, there's no, there doesn't seem to be any kind of kinetic energy when the spring is compressed. It should be stopped. So I'd say initially K should be 0.
Absolutely. And then what do you think about the U initial?
As far as U initial is concerned, I think we only have spring potential, but not gravitational potential. So we're looking at the 1/2 kx squared equation because the spring is compressed.
Absolutely. As far as the U final and the K final are concerned, we also don't have any velocity at the very end when the block has been pushed, since it goes down to rest. So that's 0 as well, and the UF should be 0 since it has no height, as we discussed in the previous problem.
So you're saying that when the spring is released, there is no potential gravitational or elastic?
I do not believe so. There should not be any potential energy, any energy at all in the system.
Okay.
So we have our equation, as you mentioned, of the ui being half of kx squared, where k is our spring constant and x is the distance that the spring is compressed, plus the work non-conserved equals to 0. And what are your thoughts about the work non-conserved in this case, Freya?
So I think this is exactly like the problem we did before. The only work non-conserved would be the friction due to the surface. And as we're solving for a coefficient of friction, we know that there is friction there. So I would say that our work non-conserved would again be mu mg.
All right, so let's put it down. And do you think it would be positive or negative?
I think negative, because again, it's acting against the object. And this would be times our distance is equal to 0.
Absolutely. So now using our algebraic equations, we can isolate the mu, or we could, do it in 2 steps, take the mu and g times distance to one side, and then isolate the mu like that.
Okay. So this gives us that mu is equal to 1/2 times kx squared over mgd.
So do you think we know all the quantities here? So
I think so. So k is our spring constant. We have that. X is our compression. We have that. Mass and gravity are known, and distance that it travels, again, is known. So I believe we could solve for mu.
certainly. So when we put in our values, which is 1/2 of 100 times 0.2 squared divided by 0.5 times 9.8 times 1. We get a final answer of 0.41. And do you think there'll be any units here?
No, as we know, we could trace this using our answers that we plugged in, and we would see that the units cancel. But seeing as this is a friction coefficient, and whenever we get friction coefficients, they are unitless, I would assume that there are no units.
Absolutely. Absolutely. But that was it for the question on my end. Did anybody have any questions, or did you have any thoughts, Fred?
Just keep in mind that checking your units at the end of a problem is a great way of seeing if you're on the right track. Because if I ended up with units when I wasn't supposed to, and the units didn't cancel out, I would know that I was doing something wrong. Whereas the fact that the units did cancel out tells me that there's a good chance I did the problem correctly.
I think we're good to move on to the next problem.
Okay. So if anybody has any questions, let us know. Otherwise, we'll move on to the next problem. So our third example here is going to deal with springs. So we have a box of mass M, which is held at a height above the spring of 8 meters. The natural length of the spring, so the length of the spring when it is not compressed, is 1 meter, and the spring constant is 1,000 Newton meters. The mass of the box is 5 kilograms. So the box is released from rest at a height of 8 meters. It is dropped onto the spring where it compresses the spring a certain distance and then bounces back up. The questions here are, what is the speed when it first reaches the spring? What distance does the spring compress? And then what height does the box reach after bouncing off of the spring? So we're going to solve all of these parts, and I will move this over to the whiteboard so that we can work on it. Okay, so for this problem here, we have a spring and a box dropped. So the spring is 1 meter high, the box is dropped from 8 meters, and it is 5 kilograms. Plus K is equal to 1,000 Newton meters. So those are all of the information that we are given at this point. I'm going to label the point where the box is in the air as point B, as point A. When it first touches the spring, I'm going to call that point B, and when it compresses, I'm going to call that point C. So that's some point. So for part A, what is the velocity at B, basically? What is the velocity when it first touches a spring? That is the question that we're being asked. So given the fact that we're looking at a spring here, and we have initial height and the variables we're given, which kind of equation do you think we would want to use to solve this, Bhavdeep?
Well, given that we have all this, we used a conservation of energy equation in the last problem, where I represent potential energy change into kinetic. And since we have an initial height, I think that would be ideal.
Right, so our conservation of energy equation is definitely where we want to go with this. I'm going to separate our different types of potential energy because, as we know, we're dealing with a spring that will come up in this problem. So I'm going to label this as UGA, UEA, and kinetic energy A. So this is gravitational, elastic, and kinetic. And then, is there any work non-conserved in this problem, Bhavdeep?
I don't think so, honestly, since it's working under gravity, and that is I mean, if you're ignoring air resistance, I don't think there is any non-conserved force.
Yeah, so we're going to ignore air resistance in this problem. So I'm going to leave work non-conserved out as there is nothing else acting on it. And I'm going to label the other side the same way. So looking at this problem, which values from the first half of the problem do you think we could cancel out?
We don't have an elastic potential energy because there is no spring at the top. So that definitely should go. And if it starts from rest, then I believe the kinetic energy doesn't exist as well.
Yes, exactly. So it's not compressing the spring when it's first dropped, so there is no elastic energy. It's not moving, so there's no kinetic. And looking at the second half of the equation, are there any values you think we could cancel out?
At the instant it touches the spring, I don't think there is a need particularly to consider our elastic potential energy.
Exactly. So when it first touches a spring, there is no compression, and no compression means no elastic energy. So that leaves us with our gravitational potential at the beginning is equal to our gravitational potential at B plus our kinetic energy at B. So writing that in terms of our variables, we get mg h at A is equal to mgh at B plus 1/2 mvb squared. And seeing as we're solving for VB, this is a good sign. We have a variable that we need in the equation. I'm going to cancel out m as it is present all across. And with the rest of the variables in this problem, can I solve for this, or am I missing anything?
I believe you have everything. So find out.
Okay. So plugging in my values that I know, I have 9.80 meters per second squared for gravity times my height at A, which is 8 meters, is equal to 9.80 meters per second squared times my height at B, which is the uncompressed length of the spring, which is 1 meter, plus 1/2 times VB squared. So if I use my algebra to rearrange and solve for this, I get a value of 11.7 meters per second. And that is the speed that the block is going at the instant it touches the spring. So again, we just used our conservation of energy equation, plugged in our known values, canceled out anything that didn't apply, and it really simplified our problem for us and made it easier to solve. Do you have anything to add to this, Bhavdeep, before I move on to part B?
Nothing particular on this part, just to watch out for what exactly is happening. I guess visualizing. Got a bad throat. Just visualizing the problem would help, so that way you could realize that when it hits the spring, there is no compression, so you can take out the quantity of UEV.
Yeah, that's a great point. It's a really easy mistake to make when it's first touching the spring to assume that there is elastic energy. But seeing as our equation for elastic energy is 1/2 kx squared, if there is no compression, such as when it's first touching the spring, if this value is 0, your energy must be 0. So that's a really important thing to remember. Okay, so I'll move on to part B now. So at part B, I'm going to draw the spring again. We have a spring that is 1 meter, and it is compressed a certain distance, x, which we don't know. That is what we're solving for. So part B, the question is, what is x, basically? What is the compression? What is x max? And again, we're looking at a problem that involves energy. We're looking at the compression of a spring. It's a good, safe choice to say that we are going to be using our conservation of energy equation. So if the top here where it first touches the spring is point B, and actually in this problem, I'm going to continue to use point A when the block is first dropped. And when it is compressed, I'm going to call that point C. And the reason for this is because when the block is first released from rest, there's only one type of energy present, meaning that I can use the potential energy at point A to determine how much energy is in the system total. So using my conservation of energy equation, I'm going to say that my potential energy at A, again, is equal to, if I write out my energy equations, I have UG at C, sorry, plus UE at C, plus K at C. And looking at the right half of this equation, Bhavdeep, do you think there's any values that we can cancel out?
I believe that the Kc should go away because we don't really have velocity when the spring starts compressing. However, that should be the only one, since we will have some sort of height, given that x is less than 1.
Mm-hmm. Right. So even when a spring is at its maximum compression, I mean, if anybody's ever held a spring in their hand, even when you compress it fully, there's still some height. You can't make the spring disappear. So there will still be some height, meaning some potential gravitational. However, it moves downwards until it stops at max compression, and the fact that it stops means that there will be no kinetic. So this is our equation. We have potential at A is equal to potential gravitational at C plus potential elastic at C. So again, I'm going to write this in terms of variables. So mgh at A is equal to mgh at C plus 1/2 kx squared. Do you see any problems with this equation, Bhavdeep? Any variables that I don't know?
We don't have the spring constant. No, the K in this case.
Oh, sorry, I should have written that down, but that is 1,000 Newton meters. So we have the spring constant, but do we know what the height is when it's at point C, or the height when it's fully compressed?
I believe we do. I believe it should be the length of the spring minus that much, minus x, which is maximum pressure.
Exactly. So we don't necessarily know it as far as a numerical value, but we can rewrite it in terms of things that we do know. So, for instance, if we've got the spring here, and the spring is 1 meter total, and it's compressed a certain distance x, this here is the height, the distance from the ground to where the spring is compressed. We can rewrite the height at C as 1 minus x. And seeing as we are solving for the value of x, this will allow us to solve the problem with a value, whereas before we didn't know what the height is at C, seeing as we don't know what the compression is. So rearranging, doing this again, we have mgh at A, so mg times 1 minus x plus 1/2 kx squared. So now our problem is entirely in terms of variables that we know or are solving for, and we can solve. So plugging in our values, that gives us 5 kilograms times 9.8 times the height that it's dropped from, which we know is 8 meters from the previous problem. And again, 5 kilograms times 9.8 times 1 minus x plus 1/2 times 1,000, which is our k value, times x squared. So now we are just left with x as an unknown, and we can rearrange this problem into a format that is actually going to look, well, if you notice that you have our variable is squared here and a power of 1 here, that gives us an indication that we're going to need a format such as ax squared plus bx plus c. So if we rearrange this, we get 500 x squared minus 49x minus 343 equals 0. So this is our A, B, and C values, which we will plug into our quadratic formula. So I will clear the whiteboard to give us a little bit more space to work. Okay, so we have 500 x squared minus 49x minus 343 is equal to 0. And this is A, this is B, and this is C, using our ax squared plus bx plus c formula. And as we know, our quadratic formula is negative b plus or minus the square root of b squared minus 4ac all over 2a. So if we were to plug in our values from above into this quadratic formula using a calculator, it would give us one viable option for x, which is equal to 0.879 meters. So this would be our answer to the problem as far as what the maximum compression of the spring is. It would compress about around 0.9 meters, which, given the fact that the block is dropped from a reasonable height and has a decent velocity when it meets the spring, that answer seems to make sense. It seems reasonable. It also is less than the full length of the spring, which is 1 meter, so that's a good sign. Do you have anything to add to this, Bhavdeep, before we move on to part C?
Not really. I mean, it's just problems with quadratic equations can be complicated, but not really. I mean, you got to solve them at the end of the day.
Mm-hmm. Quadratic formulas can be a little unavoidable at times, but they will come up. But yeah, as long as you check your answers and they make sense reasonably within the scope of the problem, that's a good sign. So part C is max height after leaves spring. So after it leaves the spring, what is the max height that the box will go to? So it bounces and then it goes back up. Now, based on the fact that there is no work non-conserved in this problem, Bhavdeep, what do you expect the max height of the spring to be?
It should be, if there's no work non-conserved, it should be the same as where it was dropped from.
Exactly. So there's nothing taking energy away from this problem. So when the box bounces back up, it should go back to its initial height. But let's just double check this with our conservation of energy equation. So if I say when it's dropped initially, I'm just going to call that initial. We have determined that the only thing present was potential energy, potential gravitational energy. And again, writing out our problem, if I say final is where it bounces to afterwards. At the end of its, as we know from projectile motion or from objects thrown upwards, when they are at the top of their arc or at their max height, they have zero velocity, so we can cancel out kinetic. And as we know, it's bouncing off the spring, meaning no compression is happening. So again, our elastic energy is zero, meaning that mgh initial is equal to mgh final. Cancel out mg, and we get h initial is equal to h final is equal to our 8 meters. So yes, we expected that it would go to the same height, and we can prove that mathematically. As there is no work non-conserved, no energy is lost, it should go back to the same height.
All right, so the next problem is about power, and we have a crate of a motorized car that starts from rest and moves with some sort of eastward acceleration. And that acceleration in this case is 2.80 m². And a worker assists this car by pushing the crate with force that is eastward as well. So it's an additional force kind of applied. And that is given by the equation that F at time t equals 5.40 newtons per second times time t. And we need to find out the instantaneous power supplied by this force at 5 seconds. So let's get to work on it.
Okay. So from this problem, we have a cart, right, on some kind of motorized thing that's causing it to move eastwards with acceleration of 2.80 meters per second squared.
And we have an additional force by somebody or a worker. And that's given by Ft equals 5.40 times 2.
And remind me, which direction is that force in?
That is eastward as well, so it's just an additional force.
Okay, so F is equal to, sorry, try not to write that as a frictional force. F is equal to what?
5.40 times T.
5.40 times T. Okay.
All right, so let's try to write the formula for power. Given, well, what do you think should be the force, the power in this situation? Right?
So we know that we're looking at power, and we know that it most likely has to do with work because we're looking at forces. So I would say our power equation is going to be power is equal to work delta W basically over delta T.
And we know that the work has the formula as force times the distance. So we can write that as d of fs times d over dt.
Mm-hmm. So force, and we can call distance s in this case, and write this over dt. So yeah, that's just breaking our work equation down.
Mm-hmm. Now let's consider the dt, which is just a small amount of time, and then the ds would therefore be a small amount of distance moved by this added kind of force in that small amount of time. Meanwhile, the force would remain some sort of a constant, or at least if we differentiate that, then we just find 5.40. Could we then say that this is f of ds over dt, f times ds over dt?
Yes, so as you were saying, if we differentiate it, we will end up with a constant force. So using that concept, we can rearrange our equation to look like this.
And we know, and we can now understand that we have the derivative of the distance over the derivative of the time, and what does that come out to?
So as we know, derivative of distance over time is our velocity equation. So that is f of t times v of t.
All right, so we have a force, but we need a velocity to solve for the power in this case. How do you think that we should go and get the velocity?
Well, I would say that as we're looking at velocity, maybe our kinematics would be a good place to start.
Absolutely, that's something that I was looking at as well. So we can use the equation v final equals v initial plus acceleration times time.
Mm-hmm.
And why do you think we use this equation for?
Well, looking at this, we know that v initial is going to be 0, which just leaves us with a value of acceleration times time. And acceleration is something we have, and therefore we will be given our velocity in terms of acceleration times time, which matches the format of our force.
Absolutely. So let's solve for it. The acceleration would be 2.80.
So we know that velocity is equal to 2.80 times time, which looks very similar to our format of 5.40 times time that we have for force. So that's a good indication that we could use this to do math, yeah.
Absolutely. So let's try to, now that we have a force in a certain point in time and the velocity at that certain point in time, let's try to solve for our power.
So plugging in our values into our equation.
We should get 15.12. T squared, right? And given that we need to find our power at t equals 5 seconds, we just need to plug in 5 instead of t, and we should be able to find our answer.
Okay. So I believe the question was asking at t equals 5. The question was asking for t equals 5 seconds, right?
Mm-hmm.
And so plugging in that value, we get 15.12 times 5 squared. And that gives us around 280. And what is the unit for power?
What?
Yes. So what is our unit? So that's joules per second. Okay.